Let's just dive right in. We're looking at a completely wild, almost unbelievable prediction about the future of technology today. Elon Musk believes we are literally on the verge of pulling artificial general intelligence out of the server rack and dropping it straight into the physical world. We aren't just talking about machines that blindly execute code anymore, folks. We're talking about systems that can independently learn, reason, and adapt to totally unfamiliar, messy environments.
When you hear the quote, Tesla could potentially be the first to bring AGI into a humanoid physical form, it sounds like pure science fiction, right? But here's the thing. This isn't just theoretical software anymore. Tesla is actively building the physical body, Optimus, to house this exact intelligence. You combine that metal chassis with increasingly powerful AI, and honestly, we're witnessing the birth of an entirely new category of machine.
Okay, Section 1. Defining true physical AGI. Let's get into it. So what does artificial general intelligence actually mean? By definition, true AGI requires a massive, massive leap in capability. It's not just about, generating a clever email or recognizing images of cats. It's about systems having this incredible, broad flexibility to adapt to situations they have literally never seen before. They have to solve completely unfamiliar problems across totally different, real-world domains, all on their own.
The difference in how this gets applied is just staggering. Think about it. Your smartphone assistant is absolutely incredible at answering questions or setting timers, but it doesn't wake up tomorrow and decide to become a car mechanic, right? A physical AGI operating a general-purpose humanoid robot theoretically could. It could learn to be a mechanic or a chef or a warehouse worker just through actual physical experience.
Moving right along to Section 2, translating intelligence to hardware.
Now, mapping human-level intelligence onto a heavy piece of machinery, that means perfectly mirroring biology. Think of your own body for a second. Your eyes collect info, your brain interprets it, your nervous system sends the signals, and your muscles act. They all work in perfect harmony. Tesla has to replicate that exact flow, syncing cameras, AI brains, wiring, and actuators. The digital thought literally has to translate seamlessly into a physical action.
Have you guys ever heard of More of X paradox? It's this fascinating idea in robotics where high-level reasoning is computationally pretty cheap, but basic, low-level sensory motor skills, stuff a toddler can do, are incredibly difficult to program. Just picking up a coffee cup requires a robot to instantly answer dozens of hidden computational questions. What's the approach angle? How hard should it grip? Is the cup full or empty? Is it slipping? All of that math has to happen in a fraction of a second. And to make it even harder, all of those calculations have to happen in messy environments. Traditional robots, they thrive in highly controlled factories where every single part is bolted to the exact same spot. But human spaces, they're chaotic. Objects move around. The lighting changes. Your dog runs through the kitchen. A truly general-purpose machine has to navigate that constantly shifting reality in real time.
Which brings us to Section 3, Tesla's vertical integration advantage.
So why is Tesla the one making this bold claim? Well, their whole approach relies on a massive competitive moat, total vertical integration. They're essentially building the entire ecosystem under one roof. We're talking about synthesizing the physical body with their custom hardware, the digital brain, which is fed by oceans of visual driving data, and of course, the scale. They're already aiming for a 1 million-unit production line. It's the whole shebang.
But wait, it is absolutely vital to point out here. Solving autonomous driving does not automatically solve humanoid robotics. Not at all. Driving is mostly about understanding an environment just well enough to steer through it without hitting anything. Humanoid robotics, that requires understanding the environment and then precisely, physically manipulating it in 3 dimensions. It's a fundamentally different and honestly way more complex challenge.
All right, Section 4, the reality check and the friction points.
Despite all this wild ambition, we definitely need to separate future predictions from current reality. As of today, there is absolutely no widely accepted public evidence that Optimus, or any robot for that matter, has actually reached AGI. We're analyzing a theoretical future here, folks. This architecture is heavily under development. It is not a confirmed present reality. A huge chunk of the development friction actually comes down to a very simple concept: the cost of making a mistake. Think about it. A digital hallucination from an AI chatbot, totally harmless. Maybe it hallucinates a fact and ruins a college essay. But a physical mistake, that has immediate, real-world, dangerous consequences. If heavy humanoid misjudges its grip, it crushes a product or, God forbid, injures a human worker.
Physical AI carries a risk profile that digital AI just simply doesn't have to worry about.
Because of those high stakes, traditional tech metrics go completely out the window. Like a 95% success rate, that is a massive, incredible win for a language model. But if a 150-pound metal machine drops its payload 5% of the time on a busy factory floor, that's a catastrophic failure. The reliability threshold for physical AGI has to be near absolute perfection.
And reliability is really just the start. Before we see mass adoption, the industry has to guarantee absolute physical safety. They have to dramatically lower the hardware costs to make these things economically viable, and, they also have to secure the frankly enormous electrical and computing infrastructure required to run millions of walking, thinking machines. It's a tall order.
And finally, Section 5, the ultimate impact.
Now, if they can actually solve those massive friction points, well, Musk's long-term vision flirts with some pretty mind-bending concepts. Take the von Neumann probe concept, for example. We're talking about machines possessing the autonomy, the manufacturing capability, and the intelligence to literally build more machines. Yes, it's a distant idea, but it paints a picture of a future where intelligent robotics could just exponentially accelerate global manufacturing, entirely decoupled from human labor constraints.
In fact, a lot of industry leaders believe this transition could straight up eclipse the Industrial Revolution. Think back. The Industrial Revolution multiplied our physical productivity using mechanical machines. But the AGI robotics revolution, it multiplies cognitive and physical productivity combined. It creates these versatile workforce platforms that can think digitally and act physically all at the same time.
This completely shatters our current definition of automation. Instead of a dumb robotic arm that just welds car doors over and over, imagine a single reprogrammable worker. It watches you do a task, practices the movement, learns from its mistakes, and then just does it independently. It could inspect products in the morning, move heavy pallets all afternoon, and then do facility maintenance at night.
Which really leaves us with one profound question to wrap our heads around. What actually happens to our world when the boundary between software and physical reality finally disappears? As this completely new category of machine wakes up and literally reaches out to touch our world, how will our economy, our workforce, and just our daily lives adapt? The race to build this future is already happening right in front of us. The only question is, are we ready for it?